change, in this picture if I allowed potassium to go wherever it wanted to go. So in what direction, where would it end up? And then again, have a think about how you would that picture change? Would my distribution of pluses and minuses change as well? Okay, so this is your next little task, to pause the video and have a go at drawing the next diagram, which represents repolarization. So you remember potassium ional channels open at this point. Okay, so I hope you had another go at a quick drawing, and this is roughly what you should end up with. So sodium already equalized, so that's not going to move anywhere, but potassium will move because you had very few of it on the outside and quite a lot of it on the inside, so it will want to go, on the outside of the membrane. And that would create a situation where you again have quite a lot of ions on the outside, so that would equate in plus, and fewer ions on the inside, which would create a minus on the inside. So we're seemingly back to the situation I started with, right? So that one, right? So that was my resting potential, right? So plus on the outside, minus on the inside. The only problem is, the only kind of difference here is that in resting potential, I had mostly sodiums on the outside and potassiums on the inside. But here, during repolarization, everything is pretty much, all over the place. So all my sodiums and potassiums have swapped places, and they're just about everywhere, right? So even though in terms of charge, I'm seemingly back to resting potential, but in terms of where my ions are located, I'm most certainly not. I'm kind of all over the shop here. So all the sodiums and potassiums are all mixed up. And this is where my sodium and potassium pump needs to come in. So let me just find you the next diagram, wherever that is. Cannot find it. Don't know what I've done to it. It is! Hooray! Right, so sodium and potassium pump. So this is what is being used then to sort out my sodium and potassium ions out. So you remember it's using energy pump, right? So it's using active transport, and therefore it's using ATP, which is energy which has been stored from usually breaking down glucose, right? And the way sodium and potassium pump works is every time you use one single molecule of ATP, that moves two potassium ions in, and at the same time it's moving 3 sodium ions out, right? So every time you're using one ATP, that kind of process goes ahead, right? 2 potassiums in, 3 sodiums out. And so over time, my sodium and potassium pump, and I'm not just going to have one of them, I'll have quite a few of them, they're going to be continuously moving those ions and sorting them out to the point where you're going to be back to exactly where you started. We have mostly sodiums on the outside because I'm continuously moving sodium outside, and I'm mostly having potassium on the inside, right, because that's where sodium potassium pump moves those. And so you're back to square one and you're back to resting potential. And at this point, your neuron is able to conduct the next impulse again. Now, I appreciate this is really complicated and there's a lot of steps and lots of probably very unfamiliar terminology. So I do encourage you to watch this video maybe once or twice, skip the bits where I'm fluffing my lines a little bit or searching for cards. But by all means, have another go at kind of rewatching it, pausing, making sure you kind of draw your own diagrams and really think about what each step means. Now, in my next video, I'm going to have a go at giving you kind of a model of nervous symbols. So if you're finding this topic quite difficult, make sure you watch this next video, because I think modeling this process does help you to visualize what's going on. And I'm also going to look at what nervous symbols looks in a graph form. So make sure you tune into this next video, which is going to be posted shortly. Thank you very much, and I hope you're all well, and I'll see you in the next video.